you're in the comments.
They can play the 9-point word on YouTube.
9 points.
Yeah, because I hit all constants, bro. What am I gonna do?
I played
Throw
a
a
30-point word
Throw.
with Zach,
Well,
and I had all constants.
I'm playing against you.
Yeah,
So,
you're screwed.
yeah. So, kindergartner playing with a high schooler. I know cat, bat, and mat. So, give me that.
All right. By the way, the foundation will get this far along with, we're trying to do is find out how it's possible to get into some standard relative energy and chemical potentials in our table without relying solely on the use of electrical cells. I said the other ways are based on applications of the third law, which we will take a brief look at, which we are currently doing. We made some arguments yesterday that suggested that possibly entropy is related to this omega, because we know that systems proceed to, if you take coins, for example, put them all heads up, and on a table run, another table, hammer, so some of them jump up, come down randomly, that you move away from all heads up and do some heads, some tails, and do lots of coins, and do that lots of times. On average, it'll be about equal number of heads tails. So we know systems proceed spontaneously. There's some driving force toward states of higher disorder or arrangements that have higher probability. And that's what this idea is all about. That entropy is somehow related to the probability of the parts, molecules, atoms, whatever it is, coins, being arranged in a given way. And those arrangements which can be made the highest number of ways are the most likely. And the way this tends to proceed that direction when there's a driving force to produce it. So that's the idea here. The question is, what kind of proportionality do we want? Do we want to say that the system, that the entropy of the system is just linearly proportional to the probability for this omega? You can't do that, because entropies, extensive state properties, entropy of a mixture is the sum of the entropy of its parts. Probability of the composite thing that has the other parts is not the sum of the probabilities of those, but it's the product of probabilities. So we have entities combined as sums, so that the entropy of a mixture, for example, is the sum of the entropy of its parts, and probabilities, that includes these omegas, which are not strictly probabilities. You divide them by the sum of all possible omegas probability, but they're related. Probabilities combine as product, so that we would say that omega the omega of a composite or a mixture is not the sum of its parts, but the product of its parts. We use pi in place of sigma to represent the product. Well, one way we could achieve this is to let the entropy be related proportional not just to omega, but to the logarithm of omega. Then we leave that in because we have the sum of SI, the sum of the logarithm of omega I, and that's the logarithm of the product of the million i's, and so they would have the right mathematical behaviors if we did that. So let's let entropy be some constant C, undetermined as of yet, times the number of ways that particles can be arranged consistent with the motion distribution. That is a statistical statement of the third law in its simplest form, where C is a constant. But now we have to ask, what the hell is that constant? Well, we don't have time to take up the study of statistical mechanics and go into that from first principles, but we can deduce it pretty damn easily. But we already know how to deduce. So let's consider a familiar process. I hope that that use of that word familiar is justified. And that is the isothermal expansion of an ideal gas. And we know the change of state, n moles of A is an ideal gas. It's at some pressure T1, some volume V1, is going to n moles of A, is still an ideal gas. At some lower pressure T2 and some higher volume V2, and it's at constant temperature. If we write this as an entropy equation, we write minus delta S, understanding that means delta S is the summation of V by SI bars. Now this I'm asking you to recall from your memory, or go figure it out again if you have to, that that delta S for this process is equal to what? Anyway.
Isn't it the dq over t?
Yeah, it's dq reversible over t. What did we've done this calculation 100 times. You better prepare to do it again. Isothermal expansion ideal gas. Last time I wrote it on the board was yeah.
DQ over 2.
No,
First
DQ
time,
reverse.
God knows.
Or did you make sure to say
N
yes?
R natural logarithm.
I don't have to be shy, you can just shout that out. Logarithm of T2 over V1. Remember where that came from? Do I have to do that again? I'm not going to. Gee. Have you ever noticed how, in a course like this, for example, that what you're doing today sort of builds on what you did yesterday, and that builds on what you did before, and how things sort of stack up. And when you get up here, we're talking about something, and you've forgotten all this stuff down here, it gets very confusing. Very frustrating. You and me alike. Should know that equation by now. One reason I use that example over and over again is to build up stuff like this. So that's stuff back from first principles. Okay, so that's what we get just from the second law. Result, integrating dq reversible over t. But now consider the free expansion, which which is not reversible. You just put the gas into a container, a compound container with a vacuum container on the other side, and you open the wall, and it just expands. That's not reversible. But what's delta S? It's the same damn thing. That's thermodynamics. And here's the way I imagine that again, is that we have some container here that is partitioned off so that over in the part of it called B1, and we have temperature T, and we have N molecules. So there's our system. This is state one. And over here is nothing, but there's space confined by a boundary. So that's state one. State two, and we've done this before, and God knows, you just remove the barrier, and we have what? Then we still have N, we still have T. This vacuum, I can call it volume of the vacuum. Okay? And the volume is equal to V1 plus the volume of the vacuum, which is, we'll just call it V2, the volume of the whole box. State 2. All right, for this change of state, we have this equation. I'll write down again. Maybe pretty soon we'll remember. Delta S is equal to N R log of V2 over V1. Second law statement. And we have ds is equal to C times the log of omega 2 over omega 1. Third law statement. Is that right? That's right. If S is C log of omega, delta S is C log of omega 2 over omega 1. That's it. Well, how the hell are we going to calculate these omegas? And it's not that hard for this application because we don't have to know the actual value of that number of arrangements, which is going to be a huge, enormous number. All we have to know is the relative value of state 2 to state 1. Delta S is equal to C log of omega 2 over omega 1 relative, absolute. Going to C log of omega 2 over omega 1 relative. If we just divide both numerator and denominator, the same thing. What is the probability? Molecule I, let's call it rho probability. The molecule I in state 2 is N V2. Here's the box. V2. Here's V1 over here, partitions removed. What's the probability that molecule I is in that box? If it's part of the system, then what's the probability? Yes or no? If the molecule is part of that system, what's the probability that it's in that box?
100%.
Huh?
100%.
1, yeah, it's 1, yeah. 100%. It's in there. Well, it's equal to 1. What's the probability that all of them are in there at the same time? What's that? That's 1 times 1 times 1 is 1 to the nth power, right? Which happens still to be 1. So you don't sum them up. You probability, what's the probability that a molecule I is in V1, that portion of the whole volume that we just said makes up V1. Partitions column, what's the probability that it be in V1? Us. Make it relative. This isn't hard. What is it?
It's just the ratio to volume.
Absolutely. It's V1 over V2, right? We did that way the hell back in kinetic theory. Volume of the slant cylinder, volume of the box, did all that. All right. It's clearly V1 over V2. Now, what's the probability, relative probability, that all N molecules are in V1? That relative probability must be what? Must be V1 over V2 to the N power. All right? Next schema. Yes, that is V1 over V2 to the N power. All right. Then we have delta S is equal to C logarithm of omega 2 over omega 1 relative is equal to C times the logarithm. The relative probabilities are just 1 to the n over V1 over V2 to the nth power. And that's just equal to C times the logarithm of V2 over V1 to the nth power. And that's just equal to C times N times the log of V2 over V1. And that's the third law. You can just figure that out without doing all the powerful statistical mechanics, referring those efficient functions and things that we have to learn about yet. We just do it based on what we know. Does that make sense? Delta S is still equal to N R logarithm of V2. Oh my God, those look a lot alike. That's equal to what? Those equations look a lot alike. They'd be exactly like it. They would be exactly alike. These are the same. If what? If C times N is equal to N times R. Well, or if C is equal to N times R over capital N. Now, number of moles is equal to the number of molecules divided by an old friend of ours, Avogadro's number. And so this is just equal to R over Avogadro's number, and that is just equal to what?
Okay.
Thank you. And that's Boltzmann's constant. And if we put that into our statement of the third law, we have S is equal to K times the logarithm of omega. I draw a big old box around that because that is one of the most important equations you find in science. That's a real big-ass equation. And we didn't pull it out of a hat. Doesn't have any rabbit ears on it. That equation is so important, it's such ridiculous, that Boltzmann, who figured it out, proposed it. Unfortunately, he was a very unhappy man about other things, as scientists often are in principle. But on his tomb, you go to Vienna, log in W. Well, what the hell is W? Well, that's what the authors call omega when he proposed this. That's equal K log of omega. He thought, someone thought this is the most important thing he did. He did a lot of important things with part or something. So that should tell you something. All right. So this is the statistical statement of the third law in full word. Now, using the same arguments that we did for deducing that from that expansion of the ideal gas, I mean, you can show this, I can show this, anybody can show this, if they understand what we've done thus far. Show that del S of mixing an ideal gas is just equal to the summation of Ni logarithm Xi, giving minus R times S. And I'll leave that as an exercise for you. It won't be on the test on Friday, so don't try to do it before then. But over the weekend sometime, just entertain yourself. Just say, how would I play with those normal probabilities and get that result? And it's not hard. All right. So now we have a tool we need to explore ways to get our entries in the tables of thermodynamic properties, including standard chemical potentials or molar free energies. So we note that this order for a crystal for a solid phase of a substance is less than that of its liquid phase, which is less than that of its vapor phase. We all know that. And this order of crystal does what as you lower the temperature? It either stays the same or it goes higher or it goes down. This order goes down. The order goes up. Okay. Decreases as the temperature is lowered. Crystals become more orderly. Why? Because there's less energy to jostle the atoms and molecules around, and they settle ever more neatly into the pockets that they create by their mutual interactions, the intermolecular potentials. They settle into those wells more quietly, and you lower the temperature, it just gets more and more neatly arranged. Well, the historical statement of the third law goes something like this, that the entropy that the number taking it to closer and closer to the perfect arrangement, be all heads up or all tails up. Right? As you get closer and closer to the perfect arrangement, sometimes that omega turn. How many ways can you do that?
Less.
One. And the entropy, which is K logarithm omega, goes to what? 0. That's the historic statement of second law. And the entropy of a perfect crystal at absolute 0 is, I mean, entropy is 0, the omega is 1, entropy is 0. This is the first time we've had, you don't talk about any of these variables in an absolute sense. Energy, we couldn't do that. Enthalpy, we couldn't do that. Free energy, we can't do that. Entropy, we can. So magic. All right. So the implication is that for the change of state, beginning with a perfect crystal of substance, at 0 Kelvin. I don't write 0 K because I would say you think everything's okay. At some pressure. Yeah, that'd be a constant to do that. And we take it to any other state. A is a substance. It's at pressure to a constant. It's at some temperature T and in some other state. I just put X here. It might be part of a solution, it might be a liquid, it might be whatever. It's not 0 Kelvin anymore. It's a temperature and T is constant. For this, we have delta S is equal to S at T, and whatever the composition is, minus S of the perfect crystal at 0 Kelvin. Oh, no. And what's this one? This one's 0. And that means that this is the absolute entropy. State, whatever it is, whatever the phase is, whatever its composition is. You start, remember S is a extensive state variable. If you start in state 1, go to state 2, delta S is independent of how you get there. It's S2 minus S1. If S1 is 0, then it's just S2. And if we did that, we could tabulate absolute intervals, like I said. We could tabulate them in their standard state or any of these verbiage, we got that. We add it to our table. We have another column. We got a column for standard for enthalpy. We got a column for heat capacity, We've got a column for standard chemical potential or free energy. We have a column for standard entropy, but it's absolute. The other side would be wrong. It's absolute. Okay. So we'll have to look at an example. Consider does generic HCl, hydrochloric acid. I don't mean in solution, I mean pure hydrochloric acid. standard state. It's an ideal gas. At our standard pressure and our standard temperature. So that's the first entry we'll get. The only one I worked through with was at T's. If we understand how we do this, then you can understand where all the others came from, following several paths. Well, we've got to start with HCl solid. At the lowest possible temperature. What's the chance that'll be 0 Kelvin? Well, that's a big chance of results, we know that. So how cold can you measure the heat capacity of something like HCl? Well, the time that the data I looked at did it with 16 degrees Kelvin. It could be lower than that now. That's the data I have. 16 Kelvin. Pretty cold. So you start down there. Turns out that HCl, like sulfur, remember we looked at the phase diagram of sulfur, we had 2 solid phases, an alpha and a beta. HCl is the same thing, it's got 2 phases, just on phase 1, phase 2. Not worry about what the crystal modifications are down there. And here I've drawn a sketch of phase diagram, just crudely, not to scale, just conceptually, what you have to do. Here we're starting at a very low temperature, turns out to be 16 Kelvin. And here we're going to 298, 25 degrees Celsius. It's actually 298.15, but we're going up there. And we're going to follow that path along that line. And we're going to calculate the entropy change for every step along it. This first is what? Warming the solid one. And then when we get to this point, what has to happen?
There's
We've got to have a phase transition. So here we'll have a delta S of warming. Integral Cp d log over T. Here we'll have a delta S of phase transition. Delta H transition divided with temperature transition. Here we'll have warming of solid 2. Here we'll have another phase transition, melting this time. Delta H fusion divided by the melting point. Here we'll be warming the liquid, heat capacity liquid, and ELNT from the melting point up to this point where if we imagine we had this system weighted down by a piston and it's all been in condensed phase, and at this time now can begin to build up a vapor phase. So we have the temperature at which vapor begins to appear in this apparatus. And we have a warming. And delta S is heat capacity of the vapor, d log over T, from TV up to T0. That's 7 steps. 7 tough external steps. We won't talk about the poor buggers who do this and how much work it is, but we will tip our hats to them because they've done us a service to make it cost for us to talk and just all bad kind of way about it. So begin to state 1, the low temperature. Measure the heat flows required to warm the phases and supply energy to the phase transitions on a path to this state here. Okay? Sheet there, I've already written out, so I don't have to scribble all this stuff down. So we consider the entropy changes associated with the following path along that isobaric line. We start with HCl in structure 1, state 1, at low temperature, 16 Kelvin, and we proceed up to the gas at our standard temperature, 1 atmosphere, along the isobaric path. I just said this is repetitious. These contributions include 4 warming steps. I articulated them, for which delta S is delta S isobaric warming, which is the integral of heat capacity times d logarithm. And 3 of them are phase transitions. Delta S transitions, delta progressive transition of delta H over delta H Q reversible over T. Delta H is the reversible heat flow for transition. Now the next chart, which I'm going to show the next page, summarizes these steps, and this chart is drawn to scale because I did this Excel sheet. I didn't put in all the details, got some scribbling on it as well. But here is what you guys have to go through to do that. Guys and gals, will do it. All right. Okay. There's all. So we have, imagine, we got this stuff, this apparatus, and the solids, and we start warming it. And we warm it slowly from 16K up to this temperature, and they were all spelled out. They're all spelled out over here on this diagram. This was 98 Kelvin, this is 150, nearly 159, 188, 298. So we know all those temperatures. This is that interval that I talked about. The value is 12.1 kilojoules per mole. That's on a mole basis. Per mole. Then we get here, we have an isothermal phase transition from state 1 to state 2, and the delta S is 29.5. And then we're warming again in the heat capacity order of the T from this T transition to T fusion, and it's 21.1 joules per K per mole. And then we transition from crystal state 2, modification 2 to the liquid, and delta S is the heat of fusion over the melting point, and that's 12.6 joules per K per mole. And then we warm up the liquid, generate another heat capacity, or T, turns out to be 9.9. And then we've got a great big kick-ass change in entropy here. Why is that? Because we've gone from condensed matter down here to the vapor state. And that, unless the pressure is real high, that's always a big change in disorder and a big change in entropy. And sure, there's a big chunk of 80.6 joules per K. And then we warm up the gas from this temperature, which was whatever I said a minute ago, which was nearly 190 Kelvin. We warm it up to 290, 298 and warm up. And that takes another 13.5 joules per K. Sum all those suckers up, all 7 of them, and we've got the result of 7 experimental measurements. We've gone from structure 1 to 16K to the gas state at standard pressure temperature. I sum them all up, write down those numbers, and it turns out to be, oh, here it is, 186.7 joules per K. Now, is that all we need to do? Well, no, it's not. We didn't start at 0 Kelvin. Right? So there's a 16-degree gap there where we don't have the contribution. And we didn't wind up in the ideal gas state. We wound up in the real gas state. So we have 2 things we have to do to flesh this out. We got to extrapolate down to 0 Kelvin, and maybe we can just take the curve we got and draw a line down there and do that. That extrapolation needs to be guided by some intelligence rather than just eyeballing a line. We do know how to correct for the non-ideality. We've done that when we're doing enthalpy. When we start with gas at 1 atmosphere, we keep the temperature constant, go down to very low pressure where it behaves ideal. We switch over to ideal gas in our imagination, never bring it back up on the real gas track. We've done that for enthalpy. We do the same thing for entropy. So that part's not hard. We can do that. This part about extrapolating the 0 though is a little tricky. And I guess it's beyond that here. I just said those things. So we need 2 more terms. Extrapolation from 16K from 0 to 16, extrapolation down to 0, But the delta test we want is from 0 to 16K, the heat capacity, crystal 1, D log of the T, we can go back. And correlate the correction for real gas departure from ideality, we can do that, that's not a challenge. I won't waste my time, I'll tell you a little bit about it. This first one I have talked about just a little bit. The extrapolation is the old cut, because that was some real science, and not the others not. That was some real interpretation aspect of science, not the observation. All right. So we first talked about heat capacity of solids when we were talking about the rule of Duvall T. And those guys were measuring specific heats back in the very early days of the 19th century, measuring specific heats of metals. And they found this correlation that related them to multiply them with molecular masses, or molar masses that were known, or atomic masses at that time. They were all about the same, all about 6 calories per mole per Kelvin per Celsius at that time. And we interpreted that with the kinetic electric theory and the idea of heat partition. But we said it fails if you come down below temperature. And the reason it fails is that the energy levels, these vibrators, oscillations that the molecules can take in crystal or any kind of atomic or molecular structure, are quantized, at least appear to be quantized to us. And so they can't just swing back and forth between any limits. There's certain ones that appear to swing back and forth between. Can't teach you this stuff, but it's important stuff. Well, the point is that as you lower the temperature, then fewer and fewer molecules find their way to these higher levels because they've got to make finite jumps. And the KT, the stirring state, gets smaller and smaller. KT is now sort of a rough measure of how hard they're banging into one another, jostling one another. And as they jostle more quietly, they just sort of settle down to the lower levels. And therefore, as we said, talk about the third law, you lower the temperature enough, and they will settle down in these lowest quantum states. And when you get down there, you get this electromagnetic one. Well, that knowledge can guide the prediction of how the heat capacity will vary at low temperatures for real systems, harmonic oscillators. And Einstein was the first to take this up, and he published a work on how to do this extrapolation. And he assumed that the crystal was made up of as many harmonic oscillators as there were atoms, and that they all oscillate at the same frequency. And that's pretty easy. You got it. Done the equation. Do that extrapolation. And it was used for a very short while, but it wasn't a very good result because the oscillations in the crystal, there's a spectrum. They're not all the same frequency, wide spectrum. And Peter Debye figured out a better way to make that extrapolation by including the spectrum of vibrational frequencies. I hope you get to study that sometime because it's pretty interesting, pretty exciting, and I'll just tell you what he found. third power law of the mind. So, for HCl, for example, at 16 Kelvin, the lowest measured heat capacity was 3.9 joules per K per mole. So we've got our delta S extrapolation. Then would be equal to interval from 0 to 16K of A P cubed over T. We don't have to know what A is, we can figure it out. Easy enough to put it in there. We don't have to write it down. And so this is the integral of A P squared dt, and that's just equal to A P cubed over 3 from 0 to P low, if you like. And the A P low cubed over 3 is just heat capacity at 16K over 3. So this is just equal to 3.9 joules per K per mole over 3, and that's 1.3 joules per K per mole, and we add that on. Add that on to our 186 or whatever we're all for. Add that to other steps. We had 7 other, this was the 8th one. Now the 9th one. The 9th one is about correcting for non-ideality. Close to my gas, but it's not exactly there. So we start with HCl, a real gas at the solid constant pressure, so we just call it at T0. And we go to HCl, HCl, a real gas at a very low pressure. Minus delta S for step 1 here. Then down to that low pressure. It's a real gas. Low pressure. We just say, oh, that's the same as an ideal gas. Plus delta S2 here. If you switch your imagination from real gas to ideal gas, when the real gas is behaving as an ideal gas, what's changing it to 0. That pressure's low enough that we can't tell it's not ideal gas. That's all. Just regard that. And then it's HCl. Now we're on the ideal gas track. Still at a very low pressure, and we've got to do what? We've got to bring it up to the ideal gas at T0. These are all at constant temperature, minus delta S3. So we sum them all up, and we've gone from HCl, real gas at T0, HCl, ideal gas at T0, delta S equals delta S1 plus delta S3. So look recognize by now is minus, 1 over V, times the partial of V, expected T constant pressure, times D, is equal to minus alpha V. And we know that alpha, that thermal expansion coefficient, that's a variable. Somebody has to make that. So you put that in and do that calculation. How about for the ideal gas case? Well, it's the same thing except alpha. The ideal gas case is 1 over T. So those integrals can be done. Using the experimental data for the real gas and then the ideal gas equation for the ideal gas, we get that this is equal to the interval from that shaft. We can assume T star is going all the way to 0 now. And we have alpha of the real gas minus 1 over T for the ideal gas times the molar volume times dP. And putting in the data for the thermal expansion, we get that this is equal to 2.7 joules per K per mole. Add this to the other 8 terms. When we do that, voila. So I got that same chart graph up there earlier, except now there's some more stuff on it. Down here, I've added in just step 1 where we did the extrapolation following the Byers-Hurd power law. Added on 1.3 joules per K per mole, and up here, this little bit, I said, this is the standard state, where I have an asterisk up there somewhere. Not there, that's not the standard state. The standard state is an ideal gas state. So we had to bump it up a little bit, 0.7 units. So we put 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. And all the work went in that. All the effort went in that. We got a result. And that result is, whoa. So the sum of delta SI, I is equal to 1 to 9, turns out to be exactly 186.7 joules per K mole. And that's delta S for this change of state. Standard state of ideal gas minus delta S, P0, P0. Delta S is equal to 186.7 joules per K per mole. But that's equal to summation of UI, SI, 0. And so that's equal to 1 mole times the expandable entropy of HCl gas. I just write that, that means ideal gas. There's 0 there, it means the standard state. Minus 1 mole times S0 of HCl, perfect crystal. And that's the 0. And so we have the molar entropy of HCl gas is equal to 186.7 joules per mole per Kelvin divided by mole. We've done everything according to the law. see that appendix, table 2 that I gave, you'll see all these things. You'll see enthalpy, you'll see, heat capacity, you'll see free energy, gives free energy, you'll see entities there. Out of this way or one other way. And the other way is a very exciting way that I can tell you nothing about. Other than this, that we have a branch of this science called statistical thermodynamics, or statistical mechanics. And thermodynamic properties can all be computed from the spectra of molecules, at least the gases. All be computed. And the spectra include information about rotational energy levels and vibrational energy levels, electronic energy levels. And spectroscopists study HCl gas and interpret those by the theoretical means of doing so, which is wonderful stuff to study. Spectroscopic data interpreted using the third law and statistical mathematics. And it is this. It's 186.91 joule per K. I know that this number isn't all that exciting. I know that. It doesn't do much for me. Just as a number. But if you don't sense you're at a pretty high elevation in the terrain at this juncture, and my sympathies with you. I know you appreciate other things I don't appreciate. But this should be a mountaintop experience. Don't think about it. Here we followed a path based on this classical thermodynamics, really, and determined by unfathomable amount of effort in the laboratory to collect data that allowed us to arrive at this number, this experimental number, for absolute entropy of HCl gas. And then we get it from another highly different approach, theoretical interpretation, just light that comes from interaction of light with HCl molecules, vapor phase. And they agree within 1/10 of a percent. That doesn't turn me on, but really honestly waste your time studying something. Just wasting a bunch of your time studying something. That's pretty remarkable. I'd like to tell you it's always that way. If it isn't, there are exceptions. And I'd like to take some time to tell you about some exceptions and how they can be explained. Not that it's outside the range of what we could do now. It's just I don't have time, or we don't have time. So I know what's going to happen. Whoa. That sort of takes wind out of me. However, I have to tell you that we left something out. But that's not the right answer. Anybody have a clue what we left out? There's right there, a chart out there. Can anybody see what the atomic weight of sulfur is? closer to a pure number of an integer. Why is it closer to an integer?
Because it's an
Well,
average.
it's also something we hadn't talked about. We're gonna talk about it real soon, a little bit, talk about it a little bit. Because I'm gonna tell you something about some nuclear chemistry, and the kinetics of nuclear phenomena. And then we'll have a chance to do this. Because atoms exist usually as mixtures of isotopes. You all know that. And so if sulfur is a mixture of isotopes, it's a mixture of two principally, 75.77% Cl35, 24.23% Cl37. If it's that mixture, those two, then there isn't meant to be a mixture, right? And we have omitted the mixture. Hydrogen is a mixture of isotopes too, but it's all very, very largely isotope mass one. So we'll leave that part out, we can put it in. So what is delta S of mixing? Well, by God, it's minus R times the summation of Ni log of Xi, and delta S squiggle of mixing is minus R. We divide through by the number of moles, we have Xi log of Xi. And so for this, it is minus R times 0.7577 log of 0.7577 plus 0.2423 times the log of 0.2423. And that turns out to be plus 0.460, 4.60 joules per mole. Okay. We leave that out. And it's not in the table. It's actually left out. Now why is that? Because we chemists. We're not nuclear physicists. We're not producing isotopic chains. We're not enriching uranium and things like that. If we're doing that, we'd have to include that. But in chemical reactions, you start with a mixture of chlorine isotopes and reactants, and you make some product with chlorine, and those isotope mixtures still there. So you can add and change, might add it in and then subtract off at the end. And in our wisdom, those who make the rules say, we just say that now. I don't want you to know it's better. Does that make sense? And that's done throughout the United Nations. Nuclear chemists and nuclear physicists who are working with transmutations of matter have to include that, of course. But they know that. They don't. Doesn't go to the shoulder and tell them about that. More. So, how can we use this new tool to achieve the goal we had at the outset? And that's to include free energies in this calculation. I set out to include values of free energies of things other than elements, where elements are zero by arbitrary choice. But for outside the standard state of elements, there's something else. And I said, well, we could use the third law to do that. How do we do that? So, how to use this new information. By that I mean absolute entities to obtain U zeros for substances. All right. So let's see. Remember that bar 0. We have, F's 0. We want G zeros or U zeros. And let's put in a couple of these, for hydrogen, for example. That's 0, because it's an element standard state. What's this? It's 0, because it's an element standard state. What's this? Well, you have to go through all those machinations, and the most accurate values come from the spectrum, which is very easy to interpret. And it's 130.684, and those are legitimate significant figures, because that's the kind of result you get from spectroscopy. You can't get that in laboratory where you got lots of stack of errors. And this is joules per K per mole. These are 2 joules per mole. And chlorine, Cl2. What's this? This is a gas, a standard state. P0. It's chemical potential to 0. What's it said? Got to go through those machinations for chlorine, and or get it from the spectrum of chlorine molecule. And this data is from that. This data because of the significance of the figures. Okay, and then we take HCl. All right. We know how to get this entry, and we did that somewhere, minus 92.31. We've been through enthalpies, we know where those come from. Calorimetric measurements. Yes, okay. We know the entry now, 186.91. What's that? All right. Here's the secret. Here's the secret. Is that delta H is delta G is delta H minus E delta S at constant temperature. So delta G0 is equal to delta H0 minus T delta S 0. And that's equal to summation of UI 0, and that's equal to 1 mole times U0. Well, we're talking about making HCl, so that's HCl gas minus 1 mole times 1/2 mole U0 H2 minus 1/2 mole U0 Cl2 gas. These are both zeros. And so consequently, we can get this, but we also have right here delta H. Delta H, I've calculated this. Yeah, it's 92.31 plus 92.31. Don't worry about this. You can figure this out on home. And so it comes out to be U0 HCl gas comes out to be minus 95.30 joules kilojoules per mole. All right, we can play these numbers and get that resolved, and that's what goes in here. Minus 95. So that was a lot of work. Think about something. This is not on the test on Friday, but it might be on the next